Good morning, students. We are continuing with the projectile motion, the last topic of kinematics. Although we had a very detailed discussion last time, yesterday we discussed in detail the second case in which you throw an object from the ground level. It remains in the air for a while, then it lands at the same level, and you have many questions in the exam. But before I conclude this topic and start the next chapter, chapter number 4, dynamics, I would like to elaborate a few more points about the same case, because we have questions in the exam in which the two different cases are combined. There is a situation in which you throw an object from the ground level, it rises, and you have to find the height, and sometimes it gets rebound from the wall, and at what distance it lands, we have to calculate that. So in order to have a better understanding of those situations, we discussed that question for last time. One exam question, it states that we have a wall, and from a known distance, suppose it is 20 meters from the wall, we are throwing an object at a known angle, and this object follows a curved path, and when it is exactly horizontal, it hits the wall. When it is exactly horizontal, it is at the maximum height. That means I can guess what distance it is. If I know this speed, suppose this is 12 meters per second, and this angle is known, let's say it is 45 degrees. So when you throw this, you have two components. One is horizontal component, the other is vertical component. Let me make it slightly bigger. So this is 12 meters per second at 45 degrees. So this is 12 sine 45, and this is 12 cos of 45 degrees. So you have two components in the beginning. If they tell us that this wall is 20 meters away from this point, and it gets exactly horizontal when it hits, that means we can estimate the maximum height to which it has risen. Obviously, if there was no wall, it would continue and land on the other side at the same level. So in order to calculate this height, we can use 2gs is equal to v square minus u square. If you remember, I told you when I started the discussion on this type of projectile motion, because maximum height has no vertical component, so v disappears there. When I apply this equation of motion on vertical component, this is 2 minus 9.81. This S is the height, h, this is 0, and this u is 12 sine of 45, and all this squared. So from this, I can calculate the maximum height. This, of course, will be positive because the minus signs will get cancelled from the two sides, and you have the height from this. We can also calculate the time it has taken to reach here, and that is the time in which the object has gone from this position O to this point P and hit the wall. In order to know that time, you can guess which equation we can apply from first equation of motion. From V is equal to U plus GT. This is 0 because the vertical motion has no final velocity along the vertical. The velocity is all along horizontal now, which is 12 cos of 45. So this is 0 is equal to U is 12 sine 45 minus 9.81 t. So t can be easily worked out from it. This is 12 sine 45 degree, whatever its value you can check. And this is 9.1. And this is time in seconds that this object has taken to reach here. We can even calculate this distance accurately, because I doubt if this 20 is accurate. With this velocity, with this maximum height, with this time, we might have a different value of x here. So let's calculate x as well. How long this wall is from the point of projection. And for that purpose, x is equal to Vt, but this time V is actually Vx. The x component of the velocity with which you have thrown it, and because this is initial velocity, so it is appropriate to call it ux into t. But that doesn't make any difference because this remains constant throughout the motion. So ux remains ux at all subsequent positions on its trajectory. So ux is 12 cos of 45 degree multiplied by this time that you have calculated here. This is the time in second. So you can check accurately what this distance comes out to be in meters. It might not be 20 because we have the known values of velocities, we have the angle, we have the height known. So this is something need to be accurately calculated. Yes, if it is already calculated in the question and they have given us here, then it is a correct number. But assuming it to be 20 might be wrong. Now, the question doesn't end here. They might ask you something that they have asked in one of the past paper questions. It gets reflected from here, it's rebound, and as a result of this rebound, it falls here. Like this. And suppose I know this distance. This distance could be something like 9.6 meters, suppose. 9.6 meter is the distance at which it falls back on the ground at the same level from which it was projected. So 9.6 from the wall, it hits after it gets rebound from this. When it gets rebound, it definitely has a velocity on its way back. So this velocity is to be calculated now. Calculate the velocity, with which it rebounds from the wall. it will take the same time to reach this level, uh, even if it has different velocity now. When it hit the wall, it had different velocity. When it gets rebound from it, it has different velocity, but it takes the same time to reach here because the height has remained the same. So whatever time you have calculated here, this was the time to reach this height, and this will be the same time to come back to the ground level. So in order to calculate the velocity with which it rebounds, we again use this formula. X is equal to ut or vt. Now x is known. This is 9.6 meters, and u is the horizontal velocity with which it rebounds, and t is also known. You have calculated here, and you can work out what number you have here. So u is simply 9.6 times t in seconds, and this will be the velocity with which the object gets rebound from here. So this is the complete question that appeared in one of the recent past papers. I have added a little detail in it, but it is something like this. We can also have a question in which the object is initially at a height, it comes back, it comes to the ground level, hits here, and then rises to a different height. And a similar calculation is done in that question as well. I think I'll share with you that question as a practice question, and you can try it on your own. This is all about projectile motion. I hope with this example, many things have refreshed, and it will be easier for you now to try many similar questions now. Now we are in a position to move on to the next chapter, and let's have a small introduction to it. And that chapter is dynamics. Dynamics is your chapter number 4. And it starts with the Newton's first law of motion. Newton's first law of motion states that an object at rest will remain at rest, and an object in motion will continue moving with the same speed in the same direction unless there is an unbalanced force acting on it. So there are two parts of it. An object at rest will remain at rest. This is one part. The second part is, and an object in motion, and an object in motion will continue moving with the same velocity, These are two parts. One says that an object at rest will remain at rest. The second part claims an object in motion will continue moving forever with the same velocity. When I say with the same velocity, that means it's the same speed, same direction. But this will happen with a condition, and that condition is stated in the last line. Provided there is no unbalanced force is acting on it. So there are three things now. Two are facts and one is condition. And this condition is same for these two facts. An object will remain at rest if there is no unbalanced force acting on it. An object in motion will continue moving with the same velocity forever. It will continue moving with the same speed in the same direction unless there is an unbalanced force acting on it, or provided there is no unbalanced force acting on it. So condition for the state of rest or of uniform motion is same. In other words, it's not possible in physics to tell the difference between rest and uniform motion. That is why if you are in the plane and it is moving at the same velocity, you feel no motion. You are as comfortable as you are in a room of your home. You're just like sitting on a sofa in your living room. So rest and uniform motion, which means moving with the same velocity, these are the same things in physics because both of them have same condition, and if that condition is not fulfilled, an object will not remain at rest, an object will not continue moving with the same velocity. Newton's first law of motion has no equation, no mathematical form, but it has useful concepts about force. It has useful concept about inertia. Inertia is a property of any object due to which it will either tend to remain at rest or it will tend to continue moving with the same velocity. Even when we apply a force to bring an object at rest to motion, or we try to bring an object initially moving and we want to bring it to rest, it will oppose that change. So the property of all objects due to which they oppose the change in their state of rest or of uniform motion, that is inertia. These concepts are actually derived on the first Newton's first law of motion, and that is actually the significance of this law. Fortunately, we don't have to go in that depth about this first law. You will remember, you will learn this statement by heart. You will understand, of course, what is the implication of it. But more important is Newton's second law because it is mathematical form. There are a lot of questions based on it, a lot of applications in so many situations around us. So let's quickly refer to the second law of motion. Newton's second law of motion states that the force, and I should say the resultant force or the unbalanced force, the resultant force, the resultant or the unbalanced force or the unbalanced force acting on the object, acting on an object is equal to the rate of change of of its momentum, rate of change of its momentum. The resultant or the unbalanced force that we just talked about in the first law, which has to be there in order to change the state of rest or of uniform motion, if that resultant or the unbalanced force is acting on an object, it must be equal to the rate of change of its momentum. Now, in order to fully appreciate what this law is really saying, we need to understand this term momentum, and that is actually the next topic. What is momentum? What is change in momentum? And what is the rate of change of momentum, which will be force? So, although we have learned the statement of Newton's second law of motion, or in order to fully appreciate what it actually says, we need to know what is momentum, and let's discuss momentum. Momentum is the product of mass and velocity of an object. Any object, if you stand by the roadside, you observe things passing by. There are motor rickshaws are going, there are buses are going, there are bicycles are going, even people are walking. All these objects, these animals and humans and things, all of them have momentum because all of them have mass and all of them have some velocity with which they are moving. Because we are saying velocity, it's not speed. That means momentum is a vector quantity, because when I multiply mass with velocity, the resultant quantity must be a vector. So this is the letter small p. This will always be used to denote momentum. So this momentum is a vector. This mass, of course, a scalar quantity, and this velocity is a vector quantity. So momentum will have a direction, and of course it will have the same direction in which the object is moving. So velocity means velocity, the direction of velocity will be the same that of the momentum. What are the units of this quantity, momentum? We can clearly see the units of momentum are kilogram, because this is mass, and this is velocity, so meter per second. So kilogram meter per second, sometimes they give these units in the multiple choice questions and they ask you what is this quantity. So kilogram meter per second, you can readily identify this is mass and this is speed or velocity. Will have same units, meter per second, but momentum, because there is no mass multiplied by speed, there is no quantity, such quantity in your syllabus, so it will always be mass multiplied by velocity. So kilogram meter per second are the units. But a more popular units are Newton second, Newton into second, and we have to show that kilogram meter per second is same as Newton second, which you can readily prove. This is kilogram meter per second square times second. So this is power 1. So this simplifies to kilogram meter s minus 1. So it is same as this. So Newton second, with which we started, reduces to kilogram meter per second, which means these two are the same units. So Newton second is more convenient to unit, and you will often see that in the statements of the questions. This is momentum. That means if an object is moving to one direction, suppose this is its mass, m, and this is its velocity, u, its momentum is mu, m into u. But if there is another, let's say this is m1 u1. Suppose there is another object that is moving in this direction, its mass is m2, but it is moving from the opposite direction and its velocity is u2. What is the momentum of this object? If the momentum of this object is m1 u1, the momentum of this is minus m2 u2. So this is the momentum of an object because this is positive. Conventionally, the positive x direction is taken positive, and if the object is seen to be moving to the left, that is in negative x direction. So minus m2 u2 is the momentum of this. If, as we have many questions in the exam, we'll discuss them later on, we'll often calculate the total momentum of two interacting objects. If they are approaching each other from opposite directions, one is going from this, the other is coming to this direction, the total momentum of these two interacting bodies is this minus this. So it is just like adding two vectors. If one vector is having this direction and the other is opposite direction, you add them with plus minus signs, and of course if this is larger value, you have the positive answer. So this is how you calculate the momentum of a single object or of several objects which are interacting. But fortunately there are not many objects involved. It's most of the time two objects that you have to deal with. Now, what if an object goes like this and hits a wall? This same object continues, and let me remove these subscripts to make things easier. This is a wall with which this object hits, and it returns with the same u. Of course, it's the same ball, so mass is not expected to be any different, and velocity may be different, but if it is a special type of collision in which it has lost no energy whatsoever, it rebounds from this wall with the same velocity but in the opposite direction. So as I said in the beginning, this is initial momentum mu, and the final momentum is minus mu because of the opposite direction. Now, what is the change in momentum now? From this example, it will be easy to remember that change in momentum is final momentum P final minus P initial, or simply PF minus PI. PF is minus MU, and this minus the formula, and this initial is MU. So change in momentum is actually minus 2 times mu. And this is the last thing for today. We learned what is momentum. It is the product of mass and velocity. But since it's a vector quantity, will be particular about its sign. If it's moving towards right, conventionally it is taken positive. If it is moving to the left, it's taken negative. And if change in momentum is to be calculated, we carefully see and calculate what is the final value of momentum, what is its sign, and with minus sign in the formula, we write the initial momentum mu. If it happens to be positive, it will remain positive, and due to this negative sign, this will also be a negative quantity, and this becomes negative because of the reason I have stated earlier, the change in direction. So the two becomes the same sign, so they add up. So the interesting result comes that change in momentum is bigger than initial and final momentum separately calculated. Initial momentum is mu, final momentum is minus mu. So magnitude wise, both have the same values, but change in momentum is twice as big. So this is an important thing to remember, and this happens during collisions. If an object suddenly changes its direction, the change is large, and it is due to the change in momentum that the object experiences a force acting on it. As Newton's second law claims, that it is the rate at which this change takes place that is equal to the force that acts on this object. But this we'll discuss when we meet next time. Thank you.